Getting better at this. I'm going to pick up here. This is slide number 31 out of 46. That's awful. So, be very careful to use shading this time. It's a really interesting confidence region. So before we talked about resampling, what we found is the way the weights are calculated, they're calculated by recursion, but it's a multiplicative recursion. And the weights are non-negative. So if it's multiplied by one number that is really small, then it really drives that weight to a very small value. And what you find is that all of the weights decay exponentially. They decay at a very rapid rate towards zero, and one of them decays just a little bit slower than the others. But because it's exponential decay, it ends up being much larger than all the others, especially since we normalize them so that their sum is equal to 1. And what that means is that when we estimate what the posterior marginal density looks like, and we look at basically the shading to tell us where the probable regions where the state is, what it does is it decays after a few samples. It decays where only one particle is being used. And it's hard to see. Why not here? Gosh, it doesn't even look like this thing is in focus. In any case, each of these is basically a single Gaussian distribution centered at where the particle mean is, and we've only got one particle being used, and we're just estimating that essentially as one Gaussian term located at that center. None of the other particles are being used. That was the problem we ran into. You want a power cycle? Go ahead.
No, I mean the focus. Maybe we can do something about
sure.
That's what I was trying to say.
Yeah, that is better. Thank you.
Better?
Much better.
I can also move it up a little bit, I guess. Do we need anything except for the slide? Maybe not.
Well, I think it's okay. Another time maybe we'll tilt it. So that was the problem that we had. And this is side-by-side comparison of what we get when we do the integral numerically and we have the optimal posterior distribution. It's very interesting, bimodal in places. And what we get from our very simple particle filter that just didn't work. And we end up with one particle and it doesn't look right at all. It's a terrible estimate. So we had problems, we saw our decayed, and again there's this multiplicative effect, and I should have written this out as a recursion of W0 times W1 times W2 times W3. When you write this out as a product, I think it becomes more clear that if any one of those products is really small, then your weights from that time forward are going to be very small. And one thing that I'll point out that is sort of a precursor to one of the key ideas when we're thinking about Q. Reed, I appreciate that you were experimenting with Q and trying different values of Q. If we could, we would want Q to be equal to P, and that way all the weights would be constant. We can't do that, but that's what we would like to do, is to pick our trajectories so that they're exactly what the the joint posterior would generate as sample trajectories. But we can't draw from this distribution. But when you think about, well, what do we want Q to be? Conceptually, one of the things that you want Q to be is to be close to P. You want to create trajectories, and you should think of it as trajectories rather than as individual points. But we want to create trajectories that are probable, so that this ratio will be close to 1. So you don't want to generate just random trajectories. I mean, one thing you could do is just say, I'm going to use the Gaussian distribution or normal distribution and have it at each step be differently. But then this ratio is often going to be close to 0 because you'll be generating trajectories that are highly improbable. In that case, you're going to drive the weights to 0 even quicker and compound your problem rather than ameliorating it. So one of the things you should be thinking about is that this is the ideal. This is the panacea. If we could sample from this, we would. And so when we're thinking about how we pick Q, we want Q to be as close to P as we can possibly make it. The closer it is to P, the better. Which basically means that when we're creating these random trajectories, we want to create them so that they're in accord with how probable they are. We want to generate a lot of probable trajectories and not very many trajectories that are improbable. I guess is another way of thinking about that. This is hard to do, but that's conceptually what you want to do. I defined this very quickly last time. Let me take a little more time to go through it this time. This is an effective tool for counting the number of effective particles. And that term of effective particles is not defined precisely other than this equation that someone made up that seems to more or less do the right things. And a lot of people use it, and I don't have any gripes about it other than that I don't know where it came from. It seems like someone just made it up as far as I can tell, which is okay because it seems to do reasonable things. So the idea here is that some of our weights are very close to zero and they're not really being used in calculating this mean or in calculating the posterior probability. And so how do we get a notion of what would this be equivalent to if all the weights were equal and we had equal weighting? What would the equivalent number be? You know, how many particles effectively do I have? And again, I'm using that term somewhat loosely. And the thing I like about this measure, in addition to more or less matching up with my intuition, is that it does the right thing in the extremes. If all of your weights are equal, and remember the sum has got to be 1, so if they're all equal, they have to have a value of 1 over np. Every one of them has to be 1 over np. And this is the ideal case. If they're all equal, then all particles are contributing equally, and the number of particles that you really have is n sub p in that case. I mean, this is how we start out. This is what we want. We want all of our particles to contribute equally, in which case the weights are all the same. They're all 1 over np. Well, if we substitute this into this equation and do just a little bit of algebra that you've probably already done in your head, then we end up, sure enough, with the number of effective particles defined by this equation as being the number of particles. So in that extreme, it does the right thing. The other extreme is when all the weights are equal to 0 except for one of them, and because the sum has got to be 1, that means the one remaining weight has got to be equal to 1. And if we take that case, we know that the number of particles that we have is really 1, because none of the others are really being used. And if you substitute 1 for just one of the weights into the sum, then you can very quickly realize that the number of effective particles in that extreme is equal to 1. And it's pretty easy to show that the number of effective particles is bounded between these two extremes that we figured out. It can't be, it's always less than the number of particles, and it's always greater than or equal to 1. And so it's in the right range. And when you look at it, it looks like the right thing. So I'm not arguing that the number of effective particles defined this way is the only way to do it. There's lots of other definitions you could come up with that would meet these 3 criteria. But this is a good one. This is the one that's used widely. So I'm just going to ask that you accept it, and that's what we'll look at and use in the exam. How are the particles actually contributing? And then we looked at this car tracking example. We initialize it in such a way that the same as the way the state is initialized. And so we start off with a full 500 particles. And then you can see how this is the plot of the number of effective particles, and you can see how it rapidly decays and very quickly heads towards, not quite 0, but to 1, and pretty much stays at 1 for the rest of the samples. And that's another nice way of seeing what's happening that's wrong. The idea that the number of effective particles, that you're only using 1, then you're wasting a lot of cycles and you're not getting any of the benefit that we thought we were going to get out of particle filters. And then this was the big sort of aha. This was an idea that was applied in this context, I think, in 1993. It was sort of got things rolling for particle filters and helped them sort of take off and become as popular as they are today. That coupled with having a lot of computer cycles available so that you could do things that took advantage of almost an excess capacity that Intel and other companies were giving us. So resampling is sort of the big idea that really moved this technology forward. And the idea of resampling, we are taking all of our particles, we're putting them in the proverbial urn, and we're taking one out, and we're not picking them at random, but we're, let me give that back. We're not picking them at random. The probability of us picking one depends on the weight that it has, and I'll explain that in a moment. We go in, we grab a particle, and then an important idea is once we grab it, we put it back. It's sampling with replacement. So after this resampling process, we have a lot of twins, or not even twins, iplicates. We have a lot of particles that have exactly the same historical trajectory. But as they move ahead, they then split off and they start becoming different as you move them ahead in time. But when we do this resampling, we're leaving some behind and we're replicating others. And that's, conceptually, that's an important idea to keep in mind, is that we are reducing the diversity of the pool of trajectories is another consequence of what we're doing, and that's good and bad. I'll say more about that in a few minutes. So, and I'll say more about how to resample also in a few minutes. But one idea that I want to get across is, when do you resample? You resample when you've got a problem. Or, alternatively, you resample when you can afford to do it computationally. The way that it's often written up is that you use the number of effective particles and you set a threshold. And you hit that threshold, you resample. There's another school of thought that says, at every time step, resample. Make it part of your algorithm. Resample every single time step. And there's pros and cons of both of these. If you're resampling at every time step, it does require some computation. And so you may, if you've got computer cycles to spare, you might be better off investing them in more particles rather than in resampling more frequently. And I don't have an answer for you in terms of how to optimize your investment portfolio. I don't know that has been determined. But there is a trade-off there in terms of computation versus how frequently you resample. And clearly the problem we saw of, we're starting off, we're trying to work with 500 particles, but if we set a threshold of 50, that means there's some time samples where really we're only getting 50 even though we're paying for 500. And so do you want to set the threshold really low, or do you want to make it higher? And I don't know that there's a lot of guidance in the literature in terms of how to do that. So these are decisions that you're going to have to make as engineers that are driving these algorithms. This is where we get into a matter of judgment and experience and maybe going deeper into the literature than I have. So the simple way is to set a threshold, and you can set that threshold so low that you resample every time step, or you can make it less frequent if you want to save some computation. I don't know how many of you are familiar with bootstrap estimation techniques, but this is a similar idea. There's a similar methodology used in bootstrap methods, which are really popular. So I just want to mention in passing that there's a whole body of statistical techniques and even books and classes on bootstrap estimation that are a close cousin to this idea of resampling. When we resample, we want the probability that we draw a particle to be proportional to the weight. Okay, so if we think of the weight's sum to 1. So you can think of this as a probability that we're going to draw that particle when we're resampling. And I've used the I star. The star just means the new ith particle. The probability that the new ith particle is going to be equal to the jth particle, that we're going to draw that trajectory. And I probably should have put 0 to n here rather than just n, because it's the entire trajectory that we're grabbing, not just the state at that particular time. So the probability that the ith trajectory, the ith particle, is going to be equal to the jth in the urn is equal to the weights. So the weights, in this case, you can interpret it as a probability. And
In the way you're describing this, is adding noise to the particles part of the prediction set?
The short answer is no. You're asking a question about how we move the particles ahead in time. How do we go from the particle at time n-1 to the particle at time n? And we do that with importance density. So we draw a sample from that importance density, and that tells us what the next step in the trajectory is. So it's not just adding noise, it's really drawing it from a distribution. And that ends up being, if it's like a normal distribution though, the way you could do that is to draw a random number from a normal distribution, scale it and shift it to that mean, and it's the same thing as just drawing directly from that distribution. But conceptually, the idea that you want to have is that we've got this importance density, we know where this trajectory came from, and now we're going to move it one time step ahead, and we're drawing a random number from a random number generator with a known distribution. And when we draw that number, that is the next point in the trajectory. That moves it one time step ahead. And that is that importance density that we talked about. Yeah? It's okay? Okay. I wish I would have taken this out because I don't... I think this is only approximately true, but I need to think about that some more. So I'm going to skip that. Eric, do you know on that? Is it true, if you draw with replacement, do you end up with an independent, identically distributed sample?
I think it's with replacement, yeah. I think so.
Okay. Yeah, I guess that is true. But I'm sorry, I can't explain this very well because it's still not crystal clear in my mind yet.
Each time is like starting the experiment over again. So
Right. Good. Okay. So, and because of that, once we do this resampling, we then can set our weights to be uniform. We're suddenly back to having all the weights being equal. They're all equal to 1 over whatever the number of particles is for these new particles after we've done the resampling. So rather than having lots of particles with very small weights, when we do this resampling, we're replicating the trajectories that are the most probable, and so they're automatically represented. You can think of it as, I showed you how we're representing this as a sum of impulses. We're having many more impulses in the concentrated areas of the distribution. So in the shaded region, we're ending up with a lot of trajectories that are in the shaded regions, and we're throwing out the ones that are far away. Now, the downside of doing this resampling, and I should have a separate slide on this, but the downside of doing this is when you do this resampling and you're drawing particles that are in the shaded region, you're now losing the ability to see what's in the non-shaded region. You're losing what's called sample diversity. You no longer have trajectories that are in improbable locations. So as you move ahead and in time, and it turns out that maybe the trajectory was going through an improbable path, you're unlikely to see it, or less likely to see it, because you are concentrating your particles, with this resampling technique, you're concentrating your particles in the probable regions. So for those of you that are tracking submarines, and a submarine could suddenly pop up in a location where maybe you weren't expecting it. If you don't have any particles there that are sort of representing that location, then you may not be able to see it. You may just have no particles there. So that's one of the downsides of resampling.
If you're doing the resampling based on a threshold of your effective number of particles, would you then, is it typically you throw out the ones that are below a certain threshold and you keep some, or do you resample all 500 based on the weight? Or to keep some, or do you just do kind of a blanket resampling?
I'm going to take a while to answer that question. It's what these next 2 slides are about. So the way this sampling is set up is the probability of grabbing a trajectory. They're all in the urn. You could grab any of them. You could grab the one with the smallest weight, but your probability of grabbing it is much less because if it's got a much smaller weight than the others. And so you want the probability that you're going to draw one to be proportional to the weights. And a simple way of doing this, one way of doing this is to this is complicated, is to draw a bunch of samples from a uniform distribution, sort them from smallest to biggest, and comparing that to a cumulative sum of the weights. This is one way of doing it, and rather than explaining even how this works, I'm going to explain how it actually is implemented in a way that's much more efficient. When you think about drawing samples in this way, this is sort of the textbook way, and the problem is that this step here is proportional to the number of particles times the log of the number of particles. It turns out there's a much more efficient way of doing it called systematic resampling. It's a really simple algorithm, and I blazed through it on Wednesday, but let me take some time to go through it now and explain how this works. First of all, let's say we've got a cumulative sum of our weights, and I'm going to try to represent that over on the edge here. I don't know if I'm going to be able to do it. I think that's probably enough to represent it. So let this be 0 and let this be 1. And in this simple example, let's say we just have 1, 2, 3, 4, 5 weights. And this thickness represents the size of each weight. So this is weight 1, weight 2, weight 3, weight 4, and weight 5. And the height of the bar, I said the width, but the height of each bar represents how big the weight is. And so let's see, C is a cumulative sum of the weights. So what that means is that C sub 1 is where this first break is. C sub 2 is where that second break is. Here's C3, C4, all the way up to C5. So we've got a cumulative sum of the weights. These particles are not ordered, but we know which weight represents each of the particles. And under this simple algorithm, you draw a single random number from a uniform number generator. And you don't want to do this a lot. You don't actually want to do this for all of the particles, because this also takes clock cycles. Random number generators are not always all that efficient. And so just drawing one random number is a nice idea. And so we do that, and then we go through, and for each of the particles from 1 to np, we increment a counter that gets incremented according to the number of particles. So in this case, we've got what I think of as a uniform sort of comb. Let's see if I can get this here. So I don't know if I can easily divide this into fifths, but it'd be something like this. Not quite uniform, but at least you get the idea. So these would be you make this U1, U2, U3, and so on. It's hard to write with this thing. So I apologize for that being so sloppy, but you get the idea. And this whole comb, these are spaced 1 over n sub p apart, but it's shifted up and down by a random amount. So where that comb sort of hits the stack depends on this initial number that is generated. And then while this is greater than our C, say if we start C0 here, then we increment the C. So if U1 lands right here, and let's say it's cutting into this stack right here, we've got another counter over here, and it goes up and it says, is this greater than U1, or it isn't? And then it goes to this one, it says, is this one greater than U1, or it isn't? And then it goes to this one, and it is. And so the first particle that it grabs is C3. And then it goes to the next U, and it says, is C3 greater than U2, and it is. So it grabs that one a second time. And then it goes to U4, and C3 is no longer bigger, and so it goes to C4, and so it grabs that one once. And then it might grab this one twice, for example. So it's a nice way of going through and selecting each of these, drawing samples essentially so it's proportional to this, and it's more efficient than the algorithm that I showed you. So this is how the resampling, a nice way of implementing the resampling. And I want to emphasize, although we're working in a single dimensional example, this process is happening on the weights. And the weights are always scalar, regardless of the dimension of your states, regardless of the dimension of your measurements. This algorithm for doing the resampling is the same, and your weights are always scalar. You've got one scalar weight per trajectory. So any questions on that, on the resampling? Okay. All right, so applying this to our example, once again we've got the true state, because it's a simulation in this case, and we've got our series of measurements. Same thing as, I think all of you have studied this code now. And this was the main slide that we stopped on Wednesday, where I was like, okay, here's how it works. And this is what it looks like. And you can visually see what's happening here. You know, this is the initial state with a certain distribution, and as you move forward, the trajectories, and this is a plot of the trajectories, not the wave. You can see the trajectories, they all sort of propagate on their own, and because this is a random walk model, they naturally diverge, as you would expect. I mean, they're all just propagating according to the state model in this case. And then we hit this point, and you can see we got rid of all of these. They were gone because they were very improbable. They had very small weights, and so when we resampled them, they simply weren't selected by that resampling process that we just went through. The ones that were up here were selected, and so then there's a lot of them now that have an identical family history, if you will. But from this point forward, they propagate on their own. They propagate independently, each of them. And so we move ahead, move ahead, move ahead. And then something cool, I think it's cool, happens here. You know, they were all just sort of spreading out. And then we hit clearly another resampling event. You can tell by the vertical stripe where suddenly a lot of the trajectories don't continue on. And you get this big hole that opens up here. And that's good, because it turns out that's a very improbable place for the state to be. We know from doing it in the optimal way and knowing what the true probability of where the state could be at that time, that it won't be there, it can't be there, that's a very improbable location. So stopping all those trajectories and replacing them with duplicates of trajectories that are up here and up here, and then letting those propagate independently forward makes sense in this example. That's something that you would actually want to do. And then you can see, you know, it continues on and does similar things as we move ahead. There's another sort of bifurcation here where it picks some that are low and some that are high, and you get a hole that opens up right here, and that's cool. I mean, that corresponds to some of the modes of the distribution. Yeah, I think this is a really nice slide for getting the idea of resampling, where you can see just the elimination. You've got all these trajectories that were going along, and then, oh, you know what, they were very improbable, so we dumped them, we got rid of them. We flushed them, we replaced them with other ones that were. And then this is also nice, where we look at just the standard deviation of the weights. You can see all the weights heading towards zero, and then we got rid of all these, essentially, that were very improbable. They could have been chosen, but they were, you know, a lot of the weights that were very small were the ones that were eliminated. And again, this works even if you're in multiple dimensions. So you can very nicely see all the different resampling events. And then this is just the number of effective particles. And you can tell, in this case, this is 500 particles, and I let it get all the way down to 50 before it resampled. So I set a threshold of 10% of the number of particles. You could set that higher, you could set that lower. You can make arguments that it should be one way or the other. I don't have strong guidance for you. I suppose when I implement this, if I'm using this type of particle filtering, I would usually tend to err on the side of having a higher threshold or even resampling every time step, if I can afford it. Just because when we're representing what's happening, I don't like doing it with only, you know, 10% or so of the particles. That seems like a lot of wasted computation to me. So I resample more frequently when I implement it, but that's just a personal choice. I don't have a reason for advising that. And Eric, do you have anything to add to that? No? Okay. So this shows, with the resampling technique, this shows what the marginal posterior distribution estimate looks like using that kernel method that we talked about last time, where you're estimating the density as a sum of bumps. And this shows where the true is, and then we've got where the particle mean is. You know, it looks much smoother. You can see a lot more particles are being used. You see it's bimodal, it's much wider. At every time slice, there are more particles, many more particles being used. We don't have that problem of it just being one. Importantly, if we compare, and I can't go back and forth with the app I'm using without driving folks crazy, but hopefully you caught it as I transitioned to this. There was just a little bit of difference as we went from the previous slide to this slide. This is the optimal one. This is computed by integrating those integrals numerically, which we can do in low dimensions, and it was really good. the side, oh, shoot. I thought I had a side-by-side comparison. Well, all right. So for those of you that are listening on YouTube, I'm afraid I'm going to go back and say a few more comments about those. So I apologize for this.